Hi everyone, welcome back to Physics 11. In this video we're going to be looking at electromotive force, or EMF for short. So we know that a battery is a source of potential difference, which we call voltage or electric energy. When not connected to a circuit, there is a potential difference between the terminals, so the positive and negative terminals. Now this voltage is also known as the electromotive force, or the EMF. Now, despite the name, this is not a potential. This is a potential, not a force. So this is because back in the day when they were studying this, they thought that those two things were the same, but they're not. So again, this is not a force; it's a potential. So again, a voltage. So for example, a car battery has an EMF of 12 volt, and let's say alkaline or any battery, let's say AAA or AA batteries, have an EMF of 1.5 volt. So however, as soon as the battery is connected to a circuit and current flows through the potential difference across the two terminals, positive and negative terminal, the terminal voltage, the V terminal, is going to be less than the total EMF. And this is because the battery itself has internal resistance. And because of that internal resistance, there's going to be voltage drop inside of the battery. So once you connect it into a circuit and now there's a flow of electrons, so there's a current, that's where that drop occurs. So that's why it says here that the voltage across the terminals will be less than just the voltage without the battery being connected in the circuit. So because of this internal resistance, the V terminal voltage is always going to be less than the EMF of the battery. So the EMF of the battery, or the epsilon, we use Greek letter epsilon, to describe the EMF instead of writing EMF, electromotive force, every time. So that's going to be the rating on the battery. So let's say you buy your AA battery, which is 1.5 volt, or your car battery, which might be 12 volt, or any other battery. The rating on it is going to be the epsilon or the EMF. Okay, so again, this is Greek letter epsilon, which is kind of like the Greek E letter. Now again, the V terminal is going to be the terminal voltage at the positive and negative terminal that you can measure with the voltmeter. I is the current, and lowercase r, notice here we're using lowercase r to represent the internal resistance of the battery. So using Ohm's law, this is just Ohm's law here, that we state that there's going to be a internal voltage drop because of the internal resistance of the battery. So V equals IR, right? So that's where that comes from. So the voltage, the rating epsilon minus the internal voltage drop of the battery. That's why we have this difference here. At the bottom, there's a note here. If the battery is not connected to a circuit, there is no current, and therefore there is no internal voltage drop. So you can only observe this voltage drop once it's connected to a circuit. So here's a schematic of how this actually happens. So consider the following diagram showing a circuit with an external resistance R. So this is our load here. So it's some sort of component. And then we have the battery. And we have the terminals A and B. So this would be your positive terminal here because that's the positive side. So this would be your plus, this would be your minus on a battery. And it shows here once it's in a circuit, there's going to be current, in this case going clockwise from positive to negative. And you're going to see this internal resistance, lowercase r, okay? And the EMF epsilon. So when you measure the voltage across the A and B terminals, the positive and negative, the voltage here is going to show so the V terminal, this is called V terminal. This is going to be less than the epsilon. So V terminal is going to be less than the epsilon. Again, because of that internal resistance that's inside of the battery. Also notice that when the battery goes dead, it's because the internal voltage drop matches the EMF. So that means that the resistance at this point is high enough that when you do your V terminal equals to the epsilon minus IR, when the V terminal equals 0, So if this equals 0, that means that the epsilon equals to the internal resistance voltage drop. So equals to that I times lowercase r. So that's where the battery is completely dead. So what can we do with this? Well, this just gives us a better understanding of how actually batteries work, and this is more accurate representation of a circuit. So we had to account for the internal resistance of the battery if we want to be precise, for example, in our circuits. Now, this is not always the case, but this gives us, again, more detailed circuit analysis. So let's take a look at a simple example. It says here that we have a 12-volt battery that has internal resistance of 0.220 ohms. What is the terminal voltage of the battery when the current is 3 amps? All right, so we know that the V terminal is going to be a difference between the EMF, so this is our EMF, so this is our epsilon, minus the internal resistance times the current. So the current is going to be I, which is going to be 3 amps, times internal resistance. So let's actually list the things on the sides here. So we're looking for the V terminal. That's what we're trying to find. So that's the question. We know the current is 3 amps, 3.00 amps. What else we know? We know the EMF, the epsilon, is 12.0 volt. Okay, and we know the lowercase r, which is the internal resistance of that battery once the current starts flowing, is 0.220 ohms. So all we have to do in this case is just plug in the values. So we're going to plug in 12.0 volts for the EMF, minus 3.00 times 0.220. Okay. Now, because of the difference here, we had to be careful with the sig figs here. So, for example, you had to do the multiplication first. So here we had 3 sig figs times 3 sig figs, so 3 times 0.22, we get 0.66. Now, this is should have 3 sig figs, so we're gonna write 0.660. So this way we keep the same number of sig figs. But because we have difference here, we're subtracting. For the subtraction part, you had to keep the least number of decimals. So our final answers will have 1 decimal place. So that's one of the common, if you remember your sig figs rules, that's one of the common places where you can lose or gain sig figs depending whether you have a difference or you have an addition. So 12.0 minus 0.66 is going to be 11.34. But again, because of the sig figs rules, we had to round to 1 decimal here. So this is going to be 11.3. And this is the terminal voltage, so the units are going to be volts. So once the battery is connected to the circuit, the voltage that the battery is going to read is 11.3 volt because of the internal resistance. And of course, the higher the current you draw from the battery, the higher this internal resistance is going to be because you're increasing the I, so you multiply by internal resistance. So it depends on the usage of the battery. All right, so what else can we say about batteries? Well, for example, if you talk about rechargeable batteries, so whenever it's being charged, like your phone, for example, the external voltage that you apply to the battery has to be actually bigger. So in order to force the electrons backwards into the battery, the external voltage must be greater than the EMF of the cell, right? Because it always goes from greater potential to lower potential. So you can't apply lower potential to the battery. It has to be greater. So in that case, the external voltage must be the sum of the rating of the battery or the EMF of the battery plus the internal resistance voltage increase. So in that case, you're adding them. So that's going to be your V terminal from the power supply. All right, so let's take a look at one more example dealing with EMF. Now in this case, we have again 12-volt car battery that has been charged by an alternator. So an alternator is basically an electric generator or electric motor that spins inside of the car that recharges the battery as the car is driving on the road. So the alternator can supply 15 volt. If the internal resistance of the battery is 1.3 ohms, what is the current through the battery? So notice here the supply from the alternator is bigger than the EMF of the battery. So here's what we know. We know the EMF of the battery is 12 volt. We know the internal resistance R is 1.3. We know the current is going to be, no, that's the one we need to find, so it's going to be question mark. And V terminal is going to be the power supply, or the alternator in this case. All right, so again, our equation in this case, because we're charging this, it's going to be the addition. So V terminal is our alternator voltage. It's going to equal to the epsilon plus the IR, because again, we're charging the battery. So we have to add that. And because we're looking for the current, we had to solve this for the I. So we're going to subtract the epsilon from both sides. So we're going to end up with V terminal minus the epsilon equal to IR, and then divide both sides by R. So I is going to equal V terminal minus the epsilon over R. So now we can plug in the values. So V terminal is 15 minus 12.0 over the resistance 1.3. All right, so again, using the sig-figs rules, 15 minus 12 is going to be 3, no decimal, so it's going to be 3 over 1.3, which means the answer should have only one sig-fig, okay, because of the rules for subtracting. So 3 divided by 1.3 is going to be 2.3 amps, but again, if you round following the sig-figs rules, this should be just 2 amps. All right, so there's a practice worksheet, 8.4, so make sure you complete that for practice. And if you have any questions, make sure you post your questions as replies on Teams.